Okay, hello everyone, and welcome to this talk on illuminating the dark metabolome. My name is Oliver Jones, and I'm from RMIT University in Melbourne, Australia. I'm a member of the Board of Directors for the Metabolomics Society, and I've helped run the Australia-New Zealand Metabolomics Network for the last 6 years now. My aim for this talk is to take you through what the dark metabolome is and how we might explore it and why we should be interested in it in the first place. Okay. Now, I'm assuming that as you've all come to a metabolomics conference, electronic or not, that you all know what metabolomics is, so I'm not going to spend time on that. But it is worth defining what I mean by the dark metabolome because it's not a term that's used an awful lot in the literature at present. Okay. So in fact, the term is something that I developed in this paper here. So I know normally in talks, you're supposed to plug your publications at the end, but in this case, I'll do it at the start. And it comes out in this issue of Metabolomics just a few months ago. So if you like the talk and you want to find out more about it, you can have a look at this paper. But in here, I define the dark metabolome as all of the metabolites that are present in a system that are either not extracted or they're not seen using standard analytical methods, and or are lost, transformed during extraction. Okay, so things that you might not extract properly, or gets transformed into something else, so you get a misleading reading. All right, so now we know what the dark metabolome is. Perhaps you're thinking, well, why do you think this is a thing? Why do you? Okay. The first one is around the sheer number of metabolites. Okay, so if we look at the human metabolome database, with the group of David Wishart's group at the University of Alberta came up with, it's now on the 4th version. This one's had a lot of computational input, and it has 114,100 individual entries. And this is about a threefold increase from the version 3.0, which had, I think, about 40 or 60,000 or so compounds in it. And as I say, this has a lot of predicted stuff, so this is not all necessarily measured compounds, but stuff that's predicted to occur. But there's also a lot of GCMS database in there and MSMS data. But the actual number of metabolites could be higher, okay? Because this is making predictions, but there's always things that it might not have caught. And if you look at the number of metabolites in the metabolome database as we go from version 1 to version 4, it's on a sort of exponential increase. And of course, in this figure, I'm not counting anthropogenic compounds, so pollutants. So if we were to measure the blood of most of the people listening to this, you'd probably find pharmaceuticals, maybe some pesticides, maybe some of the PFAS and PFOA we hear about a lot on the news, the perfluorinated compounds. I'm not going to count those in this because that gets into the expososome, which is a topic I'm also interested in, but it's not something I'm going to cover here. Okay. So what I'm trying to say here is there's a lot of stuff that might be in the metabolome. Okay. But if you think about it now for a few seconds, how many compounds do you routinely identify when you do metabolomics, or if you read a paper on metabolomics? Now, the obvious answer is the dreaded it depends. Depends if you're using NMR or mass spec, GC or LC. But I'd hazard a guess you don't see more than a few hundred at most. Okay. I know there are some studies where they have 1,000 or so, but they're a little bit rarer. Okay, so now, of course, it doesn't mean that there are 114,000 compounds in every sample that we're missing. Those are the possible things that could be there. But if we just look at one class of compounds, okay, so we've got 40 common fatty acids, we've got 40 fatty acid coenzyme A's, we've got 64,000 triacetylglycerols, 120,000 monoacetylglycerols. So you actually come out with about 69,000 compounds just from this one class. Okay. And of course, we all know that metabolites come in a wide range of concentrations, polarity, mass, and methods of detecting. So even just a small group, you get a lot of different compounds, and we're just not seeing all of these, I think, in most studies. The second reason I think we may have the so-called dark metabolome is extraction processes. So if you read the literature, there's a lot of papers that talk about what's the best way to extract metabolites. Okay, if you're using a tissue sample, for example. Most people are using methanol chloroform water extraction. That's fairly simple bucket chemistry. The question I have is, do we extract all the metabolites that are present with this? Okay, because if you look at different extraction protocols, you get different number of metabolites being extracted. And are we able to identify all the metabolites that we extract? And because we've seen, if you again look at the, you'll see that some metabolites can be transformed during the extraction process. So methanol, for example, has been shown to react with some compounds and actually transform them one to the other. And of course, some compounds are misidentified. So sugar isomers are very difficult to tell apart, for example. And when we extract metabolites, some of them they might be sensitive to light or heat or organic solvents. And if they break down during the extraction, then we won't know that they're missing. And also some metabolites are bound to proteins or lipids, so perhaps they might not come out properly. There was a study that came out a few weeks ago where they were using an enzyme, a proteinase enzyme, to break down proteins and release metabolites, but the problem was that because it broke down the proteins, it increased the level of amino acids around, so it gave incorrect readings. So we've got the sheer number of metabolites and we've got the different metabolite extractions. So if you're with me so far and you think that, okay, there is a dark metabolome, your next question might be, well, why do I care? Why bother about it? Metabolomics has been around for a long time. It's useful. It's used in a huge range of areas. Why should I care? Well, the reason I'm interested in it goes back for a long time, actually. So I work in environmental metabolomics, looking at the effect of pollutants. And if you read environmental metabolomics, you will often see something like, our results indicate that whatever experiment it was resulted in a change in amino acid levels and energy metabolism. Okay, and we have the usual suspects, so a lot of amino acids and lactate here on the end, Kevin Spacey. They get labeled as the ones that are changing, no matter what experiment's being done. And it can't be the fact that energy can't be the only thing, energy metabolism and amino acids can't be the only thing that's affected by all these different compounds. So, and this goes back a long way. So when I started in 2005, this was an issue, the usual suspects, and I think it's still around if you read the literature. The other thing I noticed when I was a postdoc back in 2005 was a lot of time when people were doing particularly bacterial metabolomics, they get a huge number of peaks that they wouldn't be able to identify because they wouldn't be in libraries. So these things would get labeled as unknown 1, unknown 2, or whatever. And I used to think, well, we must be missing some information there. So hopefully in that short time I've shown you there's a need to extract and identify more metabolites and to do it without altering their structure. The question then is how. Now I'm going to talk two ways today. So firstly, perhaps reinvigorating old technology, and that's NMR. So NMR has been a mainstay of metabolomics since metabolomics was first coined in the literature. And in fact, you could argue that I think Jeremy Nicholson's group were doing what was essentially NMR-based metabolomics or metabonomics before that. But the problem is it has sensitivity issues, and it also has a little bit of crowded spectral issues. But the sensitivity is the main thing, is that it doesn't pick up things at the lower concentrations that mass spec can. So one way might be to improve the sensitivity of NMR-based metabolomics, and there's been various ways proposed to do that. But one way I think that's exciting at the moment is DNP, or dynamic nuclear polarization, and this exploits basically electron spin. So electrons also have spin, just like protons, and you can transfer that spin and increase the sensitivity of your NMR experiments. And here's an example. So in this case, this is a carbon NMR, and it's of histidine. And you can see here that without DNP, we've got almost no signal. And when we turn on the DNP enhancement, we get a 225% enhancement in the signal. So you can see there, if we had low concentration metabolites that were being drowned out, perhaps we could increase their presence in the spectra, which would be very handy. And I think DNP is quite exciting in that way. And that would also give us the advantage we could use alternative nuclei. So normally when you're doing NMR-based metabolomics, you're doing proton NMR, but there are other NMR-sensitive nuclei, including carbon. Now normally in a sample, only C13, which is about 1% of natural carbon, is NMR active. So you need a lot more sample to get the same signal. So for example, here we have carbon NMR of mint extracts, and you can see we had 100 milligrams at the top and 2 grams at the bottom, and you can see the signal increasing as we put more samples in, more amount of sample. And you can see here, rather than being 1 to 10 ppm, the normal NMR, we're 0 to 200. So we have a lot more space to get peaks, and it's information rich. And I was quite happy when I first saw this result. This data comes from one of my third year students. But of course, as soon as I looked in the literature, I found that someone had beaten me to it. And there are a few papers using C13 NMR to do metabolomics on coffee beans. That's quite interesting. And so there are also other NMR active nuclei. Phosphorus. Phosphorus is obviously very important in energy metabolism. So if you want to actually look at energy metabolism, maybe looking at the phosphorylated compounds would be useful, because that's sort of the triphosphate bond is the energy currency. So phosphorus would be another thing. We don't really see an awful lot if you do 31p NMR today, but if you do 31p DNP, perhaps we'd be able to see a bit more and then combine that. Okay. But you will find phosphorus has been in a few studies in environmental toxicology, for example. There are a few problems with DNP-based metabolomics. Obviously, it sounds great, but there's always things that can go wrong. Or not go wrong, but make it more difficult than it might be. One of those is it's often carried out at quite low temperatures. It requires low temperatures, and you need a source of unpaired electrons to transfer the spin, and that's often done by a particular type of polarizing agent that you have to add to the sample. So totopol is one of the more common ones. You can also get solupol, which is a soluble one. But the interesting thing about DNP is it's at present there's only one DNP in Australia. That's at the University of Melbourne. But there's quite a lot of these instruments in Europe, and there's been a lot of developmental work bringing DNP, making it faster and cheaper and easily done at room temperature. Speaking to people at Technical University in Copenhagen recently, and they're doing some really interesting work with cesium-based DNP. So I think this is something that we can use to increase the amount of space that we have available in the NMR spectra, and also the number of peaks that we can see in the NMR spectra. And perhaps that will give us better information. There are some problems with it, as I mentioned. Another option we have is to create new polarizing agents so we don't rely on the totopol. One example of this could be lipophilic bioradicals based on a cholesterol scaffold. So if you had these, you could implant them into the lipid bilayer, and then any metabolites attached to the lipid bilayer, so we talked earlier about lipid-bound metabolites, we could actually get a selective enhancement of those that were bound to the lipid bilayer and study things in situ. But that's NMR. What about chromatography, which is another mainstay of metabolomics? Well, interestingly enough, although I said to you that NMR had been the backbone of metabolomics since its creation, if you look far enough back in the literature, so this paper here comes from 1966, and you can see it's a gas liquid chromatographic procedure for separating out metabolites. And they talk about trimethylsilyl esters, which we're all familiar with, and combining GC with mass spec to give a diagnostic tool. Now, of course, they didn't have the bioinformatics that we're more familiar with in modern metabolomics, so I don't know if it counts as metabolomics as such, but it does show you that people were thinking about this a long time ago. So in a sense, chromatography in metabolomics goes back further than NMR. And when people have done a bit of NMR metabolomics, they often also do some LC metabolomics or some GC metabolomics. And gas chromatography has a limitation in that the compounds need to be in the gas phase, so you need to either be using volatile compounds or make them volatile somehow. And usually that's a chemical derivatization. And that brings its own problems. What derivatizing agent do you use? How do you make sure you got enough of it? What about compounds that don't derivatize very well? So people are moving more to HPLC or liquid chromatography. And as I mentioned at the start of the talk, there have been some papers published where they have over 1,000 compounds being reported in certain sample types. But 1,000 is nowhere near the maximum peak capacity. Well, it's nowhere near the maximum number of metabolites that might be there, and the theoretical maximum peak capacity for conventional liquid chromatography is about 1,500. And you need quite a long column to do that, which means you need long run times. Now, theoretically, you could increase your column length. You could have meters or mile long columns and run one sample every 3 years. And PhD students might like that because you do run sample for your PhD. But of course, if something went wrong, you wouldn't find out for 3 years, and then you'd wasted your time. So NMR is good, but it has sensitivity issues. GC is good sensitivity-wise, but it has derivatization issues. And HPLC is good for sensitivity, and it doesn't have derivatization issues, but it does have a peak capacity issue. So there's a limit to how many peaks you can pick up with liquid chromatography. So if we could improve the peak capacity of liquid chromatography, that might be helpful. Okay, so we improve what's called the separation space. So 2D HPLC involves coupling two columns with unrelated retention mechanisms in series. So we put two columns together rather than one, and that means that the total peak capacity of the system is the product of the peak capacity of each dimension, almost. So you don't quite get peak capacity of column 1 times peak capacity of column 2, but you almost get it. And we can also hard cut particular fractions of our chromatogram. So if there's one section that's really crowded, we could split that off. So just to give you an overview, this is just a simple diagram of a normal HPLC. And you can see we have our pump, autosampler, column, and the detector. So our autosampler injects our sample, passes through the column, and goes through to the detector. With a 2D system, when the sample comes off the first column, it goes through a switching valve onto the second column and then the detector. And these two columns have different retention mechanisms. So there'd be no point doing two C18s or two cyano columns. You need a C18 here and a cyano here, or an amino column here and a C8 here. Sometimes there might also be a third pump to help with solvent issues, and I'll come back to that later. So here's just a quick diagram of what this results might look like. So if we were just to plot two columns of the same phase, so this might be two C18 columns, you'd get basically all your peaks would be where these circles are up down here. What we want is to take advantage of all of this possible separation space. Okay. Now normally when you're doing 2DLC, most of your peaks are going to come around within these two black lines. But the wider you can get the angle between this angle here, the more separation space you're going to be able to take advantage of. And what we hopefully do is, if you've got a chromatogram that looks a bit like this isn't a real chromatogram, by the way, I'm not that bad a chromatographer, but you'd be able to see hopefully that you actually had, by looking at sort of intensity maps, by mapping retention time from column 1 versus column 2, you actually be able to see that you've got, rather than 3 peaks, you've got 12 or so. And this is what the data looks like in reality. Now, obviously, 2DLC, it sounds great, but it's a bit more complicated. I haven't got time to go into all the details, but this just shows you what you can get. This is a mushroom extract, and each of these white dots here is a peak. So the data processing is a bit of an issue with 2DLC. But you can already see that this is the two normal chromatograms, and we've got far more peaks in the 2D setup. So with 2D HPLC, you get an increase in separation space, an increase in the total peak capacity. So for example, we said the theoretical maximum was 1,500. If it was 1,500 times 1,500, that gives you 225,000, which is 110 or almost 111,000 more than you need to collect to pick up all of the metabolites in the HMDB database. It's also faster, so you don't have to have days worth of sampling, and it has also an advantage that potentially, if you want to go back a step, if you imagine this is our separation space. If all of your amino acids came off here and all of your fatty acids came off here and all of your carbohydrates here, if you knew the retention time on each column for a particular class of compounds, you could theoretically, and then you ran an unknown compound, you could work out what its structure was likely to be by its retention time on both columns. So that's quite interesting. There are some things to be aware of with 2DLC. One is sample dilution. So you inject your sample onto the first column, and then you're theoretically injecting subsamples of that onto the second column. So, and then putting more mobile phase in. So it does dilute it down. Which columns to use is important. So you have to use ones with different retention mechanisms. But if you do that, then you can have problems with solvent mismatch. So you might have a reverse phase, a normal phase column, for example, and they have different solvents. And at the end of your run, you need to get your you need to recalibrate your column quick before your next fraction comes on. So if your second column starts with a mobile phase of organic mobile phase and finishes with an aqueous, or vice versa, whichever way you want to do it, you're going to have to make sure that it's all recalibrated back to the starting setup before your next fraction comes on. So those are two options, perhaps, to try and illuminate the dark metabolome. Other options, we've got databases such as MZ Cloud and the Human Metabolome Database. They've got hundreds of thousands of spectra. The creation of in-house libraries of pure compounds would be of help, but of course you can't make an in-house library of unknown metabolites. So I think some things that are going to be interesting in the future are these in silico predictive tools, so using computers to predict the NMR structure of certain things, or the MS data, and also potentially making use of existing data. So there was an interesting study that came out in a proteomics journal where they talked about the fact that a lot of spectra that were in proteomics databases were unidentified. So there might actually be a lot of data out there that we could already use. So things like metabolites, which is a repository for metabolomics data. People put their data in there. You could have a look at that and see if there's things we could identify that weren't identified before. So I think my time's almost up, so I'll finish there and just thank all the people that in my group at RMIT and the people that fund us. And thank all of you for listening. Please feel free to get in contact if you have any questions. Other than that, I hope you enjoy the rest of the conference.